Look inside almost any machine today, and you'll find a complex array of spinning gears, pumping pistons, or sliding valves. But one of the most efficient energy transfer systems ever designed handles staggering amounts of electrical pressure without a single moving part. The central challenge of our electrical infrastructure is distance. We generate raw power in massive centralized locations, but we consume it miles away in our homes, factories, and offices. Power plants output electricity at relatively low voltages. If you try to push that low electrical pressure through hundreds of miles of copper wire, the natural resistance of the metal will consume most of that energy as heat before it ever reaches its destination. Without a way to pack electrical power efficiently for travel, power plants would need to be built directly inside every neighborhood, making the modern interconnected grid a physical impossibility. To bridge those massive physical gaps, the grid relies on an automatic transmission system. This is the transformer, the device that allows us to move energy from a distant source to a light switch in a different city. The journey begins the moment electricity leaves the generator. Here, specialized step-up transformers take that raw, low-pressure power and drastically increase the voltage. This relies on a strict trade-off in electrical physics. By jacking the voltage up to incredibly high levels, the current, the volume of electrons actually flowing through the wire, drops. Lower current means less friction inside the wire, drastically minimizing the energy lost as heat over long distances. This high-voltage, low-current power can now glide smoothly across the country, suspended high in the air on towering transmission lines for hundreds of miles. But you can't plug your toaster into a 500,000-volt power line. Once the electricity reaches your neighborhood, step-down distribution transformers reverse the extreme pressure, dropping it back down to a safe, usable 120 or 240 volts for your home. These devices function exactly like the gearbox in a car. They shift the electrical pressure high for long, efficient cruising and shift it low for safe, local distribution, keeping the underlying total power intact the entire time. If we open up the casing, we find a seemingly impossible mechanism. A transformer relies on two separate electrical circuits, the primary input wire and the secondary output wire. But these two wires never actually touch each other. Instead, they communicate through empty space. When alternating current pulses through the primary winding, it acts like an electromagnet, generating a rapidly fluctuating magnetic field, known as magnetic flux, in the area around it. As this expanding and collapsing magnetic field washes over the completely isolated secondary winding, it strips electrons away from their atoms, triggering a brand new voltage and successfully transferring power across the physical gap. The degree to which that voltage changes is governed by a beautifully simple piece of math called the turns ratio. To figure out your output voltage, you just divide the number of copper wire loops on the primary side by the number of loops on the secondary side. If you want to double the voltage, you simply wind the secondary coil twice as many times.
It is a precise mathematical exchange of energy, guided entirely by an invisible magnetic field. But pushing a magnetic field through raw air is highly inefficient. The field diffuses outward, leading to heavy leakage and massive energy loss. To fix this, engineers insert an iron core directly through the center of both windings. Iron is highly permeable, meaning it acts like a tightly controlled highway that neatly traps the magnetic flux and routes it directly from the primary circuit to the secondary. This introduces a serious problem. Iron conducts electricity. If you subject a solid block of iron to a constantly fluctuating magnetic field, it generates localized swirling pockets of electricity inside the metal. These are called eddy currents, and in a solid core, they would rapidly generate enough heat to melt the entire machine. Look closely at this diagram showing how engineers solved this. The core is not a solid block of iron. It is actually built out of hundreds of paper-thin steel laminations. Every single slice is coated to electrically isolated from its neighbor. This creates microscopic physical roadblocks that stop wide eddy currents from forming, trapping the heat and keeping the system running at near-perfect efficiency. To defeat the parasitic physical forces that would otherwise destroy it from the inside out, the core has to be meticulously sliced, coated, and reassembled. When we zoom back out to the high-voltage transformers managing our massive three-phase power grids,
we see this internal physics scaled up to industrial proportions. This diagram shows the two primary ways engineers arrange these massive components. You have the core form, where windings wrap around the outside of a rectangular steel core, and below it is the shell form, where the core entirely surrounds the center windings. Wrapping the steel core around the outside like a shell simplifies the incredibly complex task of insulating the high-voltage components. It also physically blocks the heavy magnetic flux from leaking out into the surrounding air. Operating at this scale brings punishing realities. A 99.5% efficiency rating sounds virtually perfect, but if a transformer is pushing 100 megawatts of power, that tiny 0.5% of loss translates directly into massive, continuous heat radiating from the iron and copper. To survive, grid-scale units require dedicated pumps, oil radiators, and massive fans just to constantly flush that thermal energy out into the atmosphere. When you stand next to a grid transformer, its towering, house-sized footprint isn't housing moving gears. You are looking at the sheer volume of thermal cooling and electrical isolation required to safely contain megawatt-level energy. While other technologies are constantly disrupted and redesigned, this fundamental, static architecture has remained largely unchanged since the early days of global power transmission. Raw generated energy is converted into a magnetic field, scaled up or down by an exact mathematical ratio of copper wire, and safely ferried through a tightly organized highway of laminated steel. It sits motionless by the side of the road, silently translating the high-pressure energy of a power plant into the specific, steady voltage required by the devices in our homes.